Hello, IME 146 students. Welcome to week number 3's pre-lab. This week, we're going to talk all about injection molding and how parts are designed and molds are designed. So injection molding is the most popular way to fabricate plastics or polymers. Materials engineers get upset when I call them plastics. So out there, really, there's 3 different types of polymers, and really the determination of the manufacturing process depends on that type of polymer. So we're going to deal with thermoplastics with injection molding. What thermoplastics do is they heat up to produce a nice soft, formable, solid, or liquid when we're actually injecting them. Now, a thermoplastic can be remelted over and over. So what can happen is I can go ahead and reuse some of the material from my gating system in my previous mold. I can chop it up. It's called regrind. And I can add the regrind material back into my virgin material and end up basically being able to reuse my plastics, because thermoplastics can be remelted over and over. Now that's a little bit different than like thermoset plastics. Thermoset plastics have a catalytic reaction occur when they're being polymerized, and the polymers cross-link when they're actually polymerized, and they cannot remelt. So thermoset polymers go ahead and burn or char if you apply heat to them after they've actually been polymerized. So like a bowling ball would be an example of a thermoset. You can't remelt the bowling ball, you'll just go ahead and char it. Now, the third type of polymer is more of a softer polymer. It's called the elastomer. So that one, it's like urethane, or how would be an example of that. So when I made engine mounts, we made basically different durometers of polyurethane, and then that would be actually the bushing that would go inside the motor mount to absorb all of the energy or the vibration in the motor mount. So elastomers, they basically are a liquid that solidifies into a polymer. So you pour it into the mold in liquid form and it solidifies, and you have your final polymer afterwards. Now, there's lots of manufacturing processes out there used to shape polymers. I mean, you can cast polymers into a certain shape. You can do solid phase forming, like thermoforming. You can do blow molding. That's how all of our water bottles are made. There's compression molding, transfer molding. There's reaction injection molding if we're talking about thermoset type of materials. But what we're going to focus on is one of the most popular manufacturing processes for plastics. It's called injection molding. Now, injection molding really started off with the billiards contest, to be honest with you. So in 1868, John Wesley Hyatt entered a contest to replace the billiard balls material, which were made out of ivory. So pool balls are made out of ivory back then. And there was a contest that was worth $10,000 for the winner, that if you could come up with a ball that was very similar to ivory. So they tried to come up with a replacement material for that pure ivory, and they ended up inventing cellulose, or doing a cellulose processing method, and they ended up creating a plastic. It was very primitive plastic, and in order to make a round shape, they had to invent an injection molding machine at the same time. So they invented this machine. They came up with a patent for injection molding, came up with a cellulose processing method. However, the pool balls didn't bounce just right, so they didn't win the actual prize for coming up with a new pool ball, but they came up with a new manufacturing process that became really popular after World War II. So when World War II came around in the 1940s, they started making all different types of polymers out there, and they needed a different style machine compared to what the Hyatt brothers created at first. The Hyatt brothers machine was more of a plunger style, like the one we have in lab. Well, they realized that you can heat up the material a lot better if we use a screw, and you can actually get thorough heating throughout the entire melt of the plastic if you use more of an auger system or a screw system to deliver the plastic into the actual barrel. So James Henry began marketing his rendition of the Hyatt brothers injection molding machine, which used a screw to deliver the material instead of a plunger. And that's what the modern day injection molding machines now look like, a lot like James Henry's machine. I mentioned injection molding exploded in World War II. So they're coming up with new polymer materials for the process and new different styles of parts that they can go ahead and injection mold. Now, it seems like a wartime stimulate a lot of innovation in manufacturing, to be honest with you. So what happened is they have a new process now, and they were coming up with new polymers, and the industry started to blossom or explode. So this video I'm going to first show you right here talks a little bit about injection molding, and then we're going to get into the different details of the process and learn about part design and how the whole process kind of works. So let's watch the engineer guy talk a little bit about injection molding.
Injection molding is the most common method for mass manufacturing plastic products. Examples include chairs, toys, cases for consumer electronics, disposable cutlery, and my favorite, Lego bricks. Injection molding was invented to solve a problem for billiards. In the 19th century, billiard balls were composed of ivory harvested from the tusks of African elephants. This devastated the elephant population, so a billiards manufacturer offered a $10,000 prize for a replacement for ivory. And this spurred John Wesley Hyatt to develop one of the first plastics, celluloid, to create billiard balls. He patented an apparatus for molding products from celluloid. This apparatus was the birth of plastic injection molding. In principle, injection molding is simple. Melt plastic, inject it into a mold, let it cool, and then out pops a plastic product. In reality, injection molding is an intricate and complex process. An injection molding machine has three main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it rams forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute. The mold opens and the part is ejected. The mold then closes and the process repeats. All injection molded objects start with these plastic pellets, which are a few millimeters in diameter. They can be mixed with small amounts of pigment called colorant, or with up to 15% recycled material, then fed into the injection molding machine. Before the mid-20th century, injection molding machines used only external heating of the barrel to melt the plastic before a plunger injected the molten material. But because plastic conducts heat poorly, the temperature was uneven in the barrel. Either the middle was too cool and not fully melted, or the outer regions were too hot and degraded the plastic. The solution was this: the reciprocating screw, often regarded as the most important contribution that revolutionized the plastics industry in the 20th century. In the earlier plunger-style machines, plastic filled completely the cylindrical barrel. But as I showed you, the plastic was not at a uniform temperature. The reciprocating screw overcomes this in three ways. First, in modern units, the plastic fills only the space around the shaft of the screw. This eliminates the cooler central region, leaving a thinner, evenly heated layer of plastic. Second, the screw has flights that wrap around the shaft. As the screw rotates, the flights transport the raw material forward through the barrel. The flights also serve to mix the plastic. The screw action agitates the melting pellets within the flights to create a uniform mixture. And third, the screw action itself heats the plastic throughout. The shaft's diameter increases along the screw so that the distance between the wall and shaft decreases. The flights then squeeze out air as they move the plastic forward, and they shear the pellets and press them against the barrel's wall. This shearing creates friction and so heats the plastic throughout. This screw-induced shear supplies a majority of the heat needed to melt the plastic, between 60 and 90%, with the rest from the heater bands. The molten plastic flows past the front of the screw through indentations or flutes. When there's enough plastic to fill the mold at the front of the screw, it rams forward like a plunger, injecting the plastic into the mold. The plastic cannot flow backwards because when the screw pushes forward, a check ring is shoved against a thrust ring to block the backwards movement of the molten plastic. This forces the plastic into the mold. Initially, the cavity image is filled with air. As the molten plastic is injected, it forces air out of the mold, which escapes through vents. These vents are channels ground into the landing surface of the mold. They're very shallow, between 5 and 40 microns deep. The plastic, which has the consistency of warm honey, is too viscous to flow through the narrow vents. To speed the plastic solidification, coolant, typically water, flows through channels inside the mold just beneath the surface of the interior. After the injected part solidifies, the mold opens. As the mold opens, the volume increases without introducing air, which creates tremendous suction that holds the mold together. So at first, the mold slowly opens several millimeters to allow air to rush in and break the vacuum, and then the mold quickly opens the rest of the way so the part can be removed. These precision machined steel molds can cost hundreds of thousands of dollars. Removing the part from the mold can be difficult. When the plastic cools, it shrinks and so becomes stuck tightly on the core half of the mold. Molds have built-in ejector pins that push the part off the mold. The ends of the pins sit flush with the core half of the mold, but are not perfectly aligned. Sometimes they protrude or are indented slightly. So, if you look closely, you will see circular ejector pin witness marks on molded products. For example, this chair, on its bottom, has an array of witness marks. When the part drops from the mold, an operator has to remove the sprue, that section of plastic that connected the injection unit to the mold. Sprues are manually twisted or cut off the part. Sprues are attached to objects only in molds that make a single part at a time, like a chair. Smaller objects are made in multiples in a single mold. In these, the sprue connects not to the part itself, but to a network of distribution tunnels called runners. The runners fan out from the sprue and connect to each cavity in the mold via a small, typically rectangular, entrance called the gate. You can see the gate on plastic cutlery. The parts for model planes typically come still attached to their runners. Molds always have at least two parts, and where the parts of the mold meet is called the parting line. Here on this piece of cutlery, you see the parting line along the side of the fork. When mold halves close, they are never perfectly aligned, nor do they have sharp corners. This creates a noticeable parting line on the molded object. Another very important aspect of mold design is the draft angle. If a part has walls that are exactly 90 degrees, it will be very difficult to eject because its inner walls will scrape the core half of the mold. Also, the vacuum will be difficult to break because air cannot readily enter. However, if the walls are slightly tapered, even just 1 or 2 degrees, it becomes much easier for the part to be removed because once the part moves slightly, the walls are no longer in contact with the core half and air can rush in. One impressive example of injection molding is the Lego brick. You can see the injection point in the middle of a stud, but this is not from a gate or a sprue. The Lego molds use hot runners. Hot runners are a heated distribution network. This keeps plastic inside the runners molten while the plastic in the mold solidifies. This leaves no gates or sprues to be removed. The molded bricks are ejected, ready to use. The downside is that this setup is more expensive than a traditional cold runner system. On the bottom edge of the brick, you can see ejector pin witness marks. And what's most clever to me is where Lego designs their draft angle. The outside of a Lego brick must be square. So if you cut a Lego brick in half, you can see that these inner supports are thicker at the top than at the bottom. There's a draft angle of about 1.5 degrees. This helps the ejector pins push the brick off the mold. The core half and the cavity half of Lego molds are designed so that the parting line is at the bottom edge of the brick. This hides the parting line. Look around you and see how many injection molded objects you can find. Likely the device you're watching this on has injected molded parts. You should be able to find ejector pin witness marks and parting lines, but you may find something like this. It's a date wheel that shows the month and year the item was made. These are created by removable inserts and can be changed out for each run of the mold. They're very useful for tracking down defects. So to return to where this all started, John Wesley Hyatt and his injection molded billiard ball did not win the $10,000 prize. His celluloid billiard balls didn't bounce quite right. But he did pioneer plastic injection molding, a thriving, continually evolving manufacturing process which creates many billions of products every year. I'm Bill Hammack, the Engineer Guy.
All right, so I thought that was a really good overview of injection molding. If you think about it, a lot of different products out there are injection molded. So it's the most popular process for manufacturing thermoplastics. That's why we're talking about it in IME 146. And that injection mold has been machined. So we're going to talk about some advanced machining processes starting next week, like electronic discharge machining, electrochemical machining. But these advanced machining processes allow us to produce intricate details for molds. And we'll see how those work a little bit next week. But for this week, we're going to focus strictly on injection molding. So once that mold kind of comes shut and we inject polymer into it or plastic, it solidifies, and then the molds open up and the product's ejected from the mold automatically. Most injection molding machines run automatically. So where you basically have a pile of parts left over, or basically the parts are automatically placed in the bucket after molding. Our injection molding machine is like you see right up here on this slide. It's called a Morgan press. Its retail value is about $15,000 if we were to buy a brand new one. And the Morgan press uses a cylinder and a piston to go ahead and inject. So it's like the original Hyatt Brothers machine that you saw in that original patent. We're not using a screw to go ahead and deliver the material. We're using a big plunger. So our machine isn't made for high volume production. It's not made for automatic molding. It's made for more prototypes or smaller parts, and where you're not going to be producing 10,000 of the same part. You may be producing 50 or 100 parts, smaller production runs, smaller molds. And what we're going to be making are these Geneva handles like you see right here. And then we're going to drill and tap them and pretty much see what the run out is on our Geneva handles. So a little bit injection molding, a little bit of GD&T this week, some drilling and tapping, some fun stuff coming up in lab. But let's look at this Morgan press machine right here. You're going to see all the controls are on the bottom. So if we start to look at the bottom right here, the bottom's got clamp control and injection control. So there's really two main features on an injection molding machine. The clamp, which clamps the mold together, and that clamp has to withstand the injection pressure. So your mold, it has some sort of cavity. This cavity has a certain cross-sectional area on it. So I know what the cross-sectional area of this cavity is. I know how much injection pressure I'm injecting into this cavity. And if you remember the simple equation, pressure is equal to force over area, we can figure out how much clamping force we need to place on the molds to hold them together based off the amount of pressure in this area right here, in this cross-sectional area at the parting line. So that if there's 10,000 PSI in this mold, we look at that cross-sectional area at the parting line, that'll tell us how much force we have trying to split us apart right here. And to overcome that, we just make the clamping force a little bit greater than the actual amount of injection pressure or amount of force that's produced by the injection pressure. Pressure over the area equals the force. So that's going to be something we're going to have to match, or it's going to be matched for you in lab. So we have clamp pressure and we have injection pressure. We'll talk a little bit more about that later. Now there's a toggle. There's basically a mechanism up here that goes up and down. There's a toggle clamp and a ram. So when the molds actually open up like so, when it's open in that condition, when you go to inject, it closes automatically, puts that clamping pressure on there, and then the plastic gets injected in the mold, and then you end up with your part from the center of the mold right there. So that's going to be kind of what you see right here, this toggle mechanism, and then this plate that slides up and down. Now there's a simple guard. A guard is just to keep the operator safe. And then up at the top, you're going to see we have the temperature controller. So this is how we melt our material. We have a nozzle and a barrel temperature controller up there. We want to get the material in the barrel just about ready to melt. Well, we don't want to melt it, or else we'd have a big mess. We only want to melt right at the nozzle, so we don't have a bunch of polymer that's melted inside of our machine. We want beads inside the barrel that are right about ready to melt. And then at the nozzle, they'll go ahead and turn into the liquidous form and get injected into the actual mold right there. Now, these pellets, they get fed into the actual material loading chute up here in the top. And you're able to get about 2 or 3 cycles or about 6 parts out before you have to keep reloading that actual barrel or before you have to be reloading the material chute over and over there. So, and we'll show you how to do that in the lab. Now, what you're seeing right there is the last mold that we had. We had a 6-piece mold last year. And that 6-piece mold gave us a lot of problems with cycle time. The plates were a little thin and we were having trouble we had some flash issues because the plates actually weren't withstanding the amount of injection or pressure that we had in there. The plate was actually flexing and we'd get some flash. So last week I redesigned the mold set. I'll show you how I did it in SolidWorks here in a few minutes. And so I redesigned a 2-piece mold that you can just stay down on the injection pressure and it'll go ahead and make a perfect part, fill perfectly. And we won't have as many issues with actually with machine. So that's going to be, you're going to see some 6 molds, or this is going to be what you're going to make in class, a 2-person mold, or basically a 2-handle mold right there. Now, when you're designing for injection molding, the injection units would actually inject the molten plastic through the sprue. So we have a sprue, it goes down through the sprue into the runners. There's a cold well slug. At the bottom, there's always a slug or a well that catches the junk plastic that first gets injected. Usually the first plastic right out of the nozzle isn't perfect or it's not perfectly melted. So we usually have a well to capture that. And that's really what the well does. But it goes down the sprue, gets caught in the well, goes through the runners, and then through the gate into the actual part. Now, when you're sizing a machine or sizing your molds, your injection unit is normally sized so that it contains 2 cycles of material per basically in the barrel. So 50% of the barrel gets emptied during the cycle. 50% is ideal, but it's got the Pareto rule, never less than 20 nor greater than 80. So you want to be between about 20 and 80% emptying the barrel every single time with your shots, if we're talking about sizing the machine. Now, once that injection unit has a couple of different pieces that go in there. So in a real machine, you have a barrel, which is basically part of your injection unit. Now the barrel has a reciprocating screw in it and then different electric heater bands to melt that material. It's composed of a tool steel liner, and then it has either a screw or a plunger going down the center. And the press we're using has just a pneumatic plunger so we have basically a large pneumatic piston that pushes down on the melted plastic and injects it into the actual cavity of the mold. Now, there's a control unit or a computer system that looks at something called a thermocouple. A thermocouple senses temperature. So the thermocouples in the heater bands there, and the control system allow it to turn on and off and stay at a specific temperature that's really close to the melting temperature of the material. Because remember, it doesn't actually melt till it gets to the actual nozzle in the injection molding machine. So that's all the control unit does, is it keeps the barrel the correct temperature, and it allows you to open and close the press. That's part of the control unit. So it opens up, closes during the actual cycle. Now, the hopper is where you keep the plastic pellets or the polymer pellets there. So thermoplastic material is loaded into the hopper. Now, materials like nylon really like to absorb water. So there's a lot of polymers out there that absorb moisture from the air. And the problem is when the air, or when we get the moisture from the air absorbed into our material, we heat our material up above 220 degrees Fahrenheit. So water at 220 degrees Fahrenheit turns into steam, right? And if we have any type of steam, it's going to be trying to expand in our barrel, we're going to have some issues. So if you hear any hissing or popping out of your injection molder, you probably have some steam going on there, and it's not going to give you desirable results. So real production injection molding machines have a dryer on the hopper in order to always basically aerate or dry out the material as it's sitting there in that hopper, so we can get rid of that moisture. What we do is we put it in the oven at 225 degrees Fahrenheit and let it bake, and that bakes the moisture off of our material. Then we can go out there to lab and basically spoon it into our actual hopper in our machine. So dryers remove the moisture from absorbed in the actual polymer materials out there. Now, the injection unit is a screw on most machines. And so it goes from that hopper down into the screw. It gets fed into the backside of that screw, into the feeding zone. The feeding zone starts to compress the material, giving it a little bit of shear. There's some shear stresses going on in there as we're compressing the material, and that's creating heat as well. So in that transition in the metering zone, we're using the frictional shear force to heat it up along with those heater bands. And then right at that nozzle, it should melt and inject right into your actual cavity of your mold. Now, most injection molding machines have a spherical radius for their bushing. So looking right out here on my mold, that's a spherical radius. So it's a radius in the form of a sphere. there's a hole, so it goes down into the actual cavity of the mold. Let me show you the mold here. Open that back up. So you can see on the opposite side of that sprue bushing is the actual reverse taper sprue that'll feed the mold, and then the gates and the runners right there. So the sprue bushing comes in and attaches itself to the top of the mold. Pressure's placed on that. It's got that concave radius, and it doesn't allow plastic to leak out. This way it goes out down into the actual mold, the path of least resistance right there. So the nozzle fits into that radius with the aid of a simple locating ring. Now, once the mold's together and clamped and the nozzle's up to it, you have to set the injection pressure on the machine. Injection pressure is really rated off of how viscous is your material and how big of a cavity do I have to fill. Do I have to fill a large cavity? Do I have to fill a really thin cavity? What do I got? Do I have a lot of passageways that might need a little bit higher temperature and higher pressure in order to fill them? Just really depends. So our press has 12,000 PSI max injection pressure. And to be honest with you, we're running 6,000 PSI. So we have 60 PSI. So we have 60 PSI injection pressure right there, which is proportional based off the machine's 12,000 PSI. So we're running about 6,000 pressure, just so you know. We're running about 6,000 PSI injection pressure. Normal practice is to begin molding around 7,000 or 8,000 PSI, and you decrease or increase based off your results on what's filling in the mold right there. Is the mold filling or is it not filling? If it's fully filling, you can keep decreasing till it doesn't, and then add a little bit more pressure so it fills again. But that's what the injection unit does. So you have a little needle control valve down there that you twist it, that adjusts how much injection pressure we actually have. Now, the clamping unit is red. The clamping unit is going to be how much force the machine is putting on the two mold halves in order to keep them together. So our machine is capable of 20 tons at 200 PSI. We can't get, we don't have 200 PSI of shop air. We have about 120 PSI. So we can't actually clamp 200 ton or 20 tons of pressure. We can get about 12 tons of pressure out of our machine. So, but when in doubt, don't ever max it out, because you can actually hurt the molds by clamping them too much. So you want to match your injection pressure and your clamping force so that your injection pressure doesn't spread out your molds when you're actually, when you inject. So that's all it really is there, to keep it together. So you have one nice congruent mold cavity that's together. It doesn't want to spread apart when you add that 8,000 PSI or 6,000 PSI into the cavity there. So that's what the clamping unit does. Now, clamping units can basically, or materials are classified by their flow. There's high flow, average flow, and low flow materials. It's a number 5 to, basically a number 5 to 20, where 5 flows the lowest, 20 would flow like water, or close to that there. So you can, based it off the amount of flow, you might have to go ahead and give it a little bit more clamping pressure as well when we have low flow materials right there. Now, our clamp, when we pick clamping right there, how they actually figure out the clamping force is they multiply the projected area by 2 to 8 tons. So low flow materials use 8 tons, high flow materials use 2 tons per inch squared right there. So we have a low flow material, so we would use 8 tons per square inch off of our projected part area, and then we add a safety factor, and that's where we set our clamping pressure so it doesn't injection pressure doesn't actually spread it apart right there. So you can see our clamping unit, when you look at the Morgan Preston lab this week, is a toggle joint. So the toggle joint comes up over center and it's ready to go. Production injection molding machine uses a large hydraulic piston. So you'll see what we got right here is a large hydraulic cylinder, and this is the actual area of the cylinder multiplied by the hydraulic pressure will go ahead and get us our amount of force that we have for clamping right there. So that clamping unit, you're wondering, why don't we just clamp it all the way or as much as possible? Well, if you use too little clamp force, the mold's not going to stay closed when you inject plastic into it. So it'll go ahead and it'll flash. So, and that flash won't look good, or you might not fill parts if it opens up because it wasn't able to flow into that cavity. If you use too much clamping force, you can damage the injection mold or crush the mold material and cause a very expensive repair or impossible to repair scenario out there. Or you could even damage the molding machine if you slam it too fast, too close with too much force right there. So those are the consequences of improper clamping pressure. So what we got here, kind of an animation. Let me turn off the sound of really what's going on right here. So when we have this box, go 1 second, let me just turn this down. So we have this box. So if you'll notice, we have our tool. These are going to be ejector pins that pop the part out afterwards. They have the full mold right there. So the way it works is you get your beads. They go on the top of the hopper right there, right? So we kind of know how this works. We put our beads in there. We put any colorant in there that we need. The hopper is going to dry it out and get rid of all of the moisture that could be in that material. So once it's dried, it goes into that screw or that auger. There's 3 zones in the screw. There's the feed zone where you first drop it in from the hopper, the transition, and the metering zone. After the metering zone, it goes into that non-return check valve. So what happens is the granules start to melt and melt and melt. They're not melted yet until they get up to that metering zone right above the check valve right there. So on the left-hand side of that check valve is where it's melted. Now at this point, the screw is going to go ahead and plunge. So the molds in the high production machines are cooled. So there's cooling channels in there to keep the mold at a constant temperature. Over time, that steel mold will heat up to the same temperature that it's injecting at. So it basically injected it. It held pressure on the mold while it solidified. And then it went ahead and opened the mold, and the actual injector pins pop the actual part out. And then it'll continue to do this automatically. These injection molding machines are an automated machine where it automatically molds your parts. You don't really have an operator standing in front of it, pushing buttons like we're going to do on ours in lab right there. So that's the full process right there of injection molding. Now, that temperature, how they actually take temperature, they don't just believe the thermocouples in the barrel. They do what they call an air shot. So in the material safety data sheet for the specific material you're molding with, it'll have the melting temperature on there. So you set it very close, you inject, and the second it comes out of the nozzle, you put a temperature probe in there in that air shot, and that'll tell you how hot it is actually coming out of the nozzle. And you can adjust based off that. So they actually do a real temperature check with an air shot. Now, on our injection molding machine in lab, we can control temperature in 3 different areas. Number 1 in the barrel, that's where we don't want it to melt. Then we can control it in the nozzle, that's where we do want it to melt. And then because we have aluminum molds, we actually have to keep our mold hot, or else it's going to cool off so quick and it would do a cold shut. So what a cold shut is if we inject our material into the mold and it hits the cold surface of the mold, it might end up solidifying before it actually fills the entire mold. So we have a hot plate that we keep at 200 degrees Fahrenheit. So our mold is always 200 degrees. The material still solidifies in that 200 degree mold right there. So we can control temperature in 3 different locations right there. Now, the pressure, if we go ahead and just max out the machine on injection pressure, we're going to get flash around the parting line. So flash is a thin layer of plastic that went outside the mold cavity where the 2 halves of that injection mold meet. So you can actually ruin a mold if you flash over many different cycles. Over time, it starts to flex the mold or wear the mold out where the plastic is leaking out of the mold. So you can actually hurt a mold by flashing it too many different times over time. That's why you really want to control your injection pressures, and we use math to figure out our injection pressure. We don't just kind of guess. We use simple math, like I explained before, with the pressures and the cross-sectional area of where we're at in our parting line, or the sectional area. Now, if we just crank it down and didn't give it enough pressure, we get what we call a short shot. So that's where the plastic doesn't actually fill the mold cavity completely. And we end up with an unfilled part, an unsellable part, or an unusable part. So that's too little pressure. Now, if you think about it, there's our mold. There's our 6 mold down there at the bottom. We remember we were going to use the 2 molds now, the new ones I made this year. But when we're talking cycle time and we're talking making thousands of parts, you got to think of all these different variables as part of your cycle time. You got to think about the time it takes the mold to close. You got to think about the time it takes to inject the plastic into the mold. You got to hold that pressure in the mold for a little bit of time while it solidifies, a few seconds. So that's the injection hold time. It's got to cool for a second or two. It's the screws got to return, or the dowsing has got to return, and then the mold's got to open. Then once the mold opens, the part has to be removed or pop out. Then we got to close again. So that's a full cycle time, pretty much gate to gate right there. So mold close time to part removal is very important, that you get all those different pieces down for your actual cycle time right there. Now what I'm going to do is to end up today's pre-lab, so you can get out there and start designing plastic parts to be moldable. I'm going to talk a little bit about injection molding part design. So really the most common failures in injection molded parts is stress. You can actually mold stresses into the part by bad part design. So if the part cools too quickly, or if it's under excessive pressure during cooling, it solidifies in a stressed manner. So if you solidify with internal stresses in your part, you're going to have problems when it actually goes to take the loads later on, because it's already stressed out. So proper part and mold design can help eliminate some internal stresses. So really the 4 areas we talk about in part design are draft, sharp corners, gate location, and then wall thickness. So number 1, the video talked about draft. When you go to pull the part out of a mold, you will get suction if you don't have any draft on your surfaces. You basically have drag on the wall, frictional drag, and you also have then suction from having a vacuum in there. So the deeper the draw of the part, the more draft is needed. So the deeper the part is, the more degrees of draft you need. So for injection molded parts, they're usually drafted, or they have an angle for their vertical walls about 1 to 3 degrees. All molded parts on injection molded machines have some sort of draft angle to them. You can get down to as little as 1/4 of a draft, although that might still be hard to inject the part. Usually they're about 1 to 3 degrees on injection molded parts. So start looking around at the plastic parts that have been molded, guarantee they have draft away from the parting line somewhere. Now, another thing that would cause stress in plastic parts or any types of parts are sharp corners. So sharp corners lead to stress rises and cracks. They're hard to machine molds with sharp corners too, sharp internal corners. So the corner radii affects molding machine time, and it's going to take a little bit longer actually to mold, and it doesn't flow as well. And then when you go to take the stress up with the part, or you go to absorb the amount of stress that's in the part, you're going to probably get a tear in that nice sharp section. So you make nice generous fillets and rounds instead of sharp corners on injection molded parts. Now this is more in gate design. So when you're designing a mold, you always want to go ahead and gate into the thickest cross section that part has. You want that thick cross section to solidify last or freeze last. So you gate into the section that freezes last right there. So it's heat transfer. It freezes from thinnest to thickest section. So the thickest sections freeze last. That's where you want to go ahead and gate into. Now, last but not least, injection molded parts do not like thick walls. You like real thin, uniform walls on injection molded parts. So if you have thick pieces, you're going to get what we call sink in your parts. So then sink basically has more shrinkage in a large section, or it warps parts. It's not a good thing. So when we start to design injection mold parts, we core the geometry. What I mean by that, if you need it to if it looks as to the left right there, like this square, you can see it's sunk, you would core it out so where you have standard wall thicknesses for everything, and you still have your same shape. So you can see original geometry, core geometry. You like to keep the wall thicknesses the same as possible throughout your injection mold designs out there. And if you have sharp transitions, you try to do them with an angle. So instead of having a sharp corner like this, you smoothly transition from one thickness to the other That way you don't have difference in cooling that's drastically different, which is going to cause basically molded in stresses. If one piece freezes at one time and the other piece is still molten, you're going to end up having molded in stresses because they didn't cool uniformly across the part right there. So wall thickness is a big thing in uniform transitions. Don't have sharp flow transitions. So there's a video link right here. If you wanted to watch Brian, our lab tech, inject the Geneva wheel handles. I'm not going to show that right now. I'm going to show you how we design the mold in SolidWorks. So you're going to get a chance to go ahead and everybody's going to use the injection molder on their own or in teams of 2 in lab in week 3. And you're going to end up making these handles. And then these handles, let's go ahead and look at the engineering drawing. These handles then are going to get turned into this Geneva handle drawing from our assembly drawing. So you're going to see we're going to mold the raw material. Then in lab, you're going to go ahead and face. You're going to center drill, and tap the thread into the part. And that thread now becomes our datum. If you look at this drawing, the A datum is the 1/4-20 thread. So everything spins around that thread if you think about it, where it attaches to the Geneva wheel in the assembly. Therefore, that's our datum. So part of this design is we didn't want the handle to be over wobbly as it spun around on the Geneva wheel, on the Geneva drive wheel. So what we ended up doing is we put a run out tolerance to the A datum on this handle. So what you're going to end up doing is you're going to mold the part. You're going to put it in the lathe and hold it in the collet chuck, and you're going to make the thread in it and qualify that A datum, the thread. You're then going to take it out of that collet chuck and put it into an inspection fixture where you hold it by the A datum or you thread it onto the fixture. And then you're going to use something called a test indicator and a holder. We have magnetic stands for our test indicators, and you're going to measure the amount of run out that your handle has. Hopefully it's less than 30 thou, or else you can then mold another handle and then make another part to see if you can get it within less than 30 thou. So 30 thou is the amount of run out. So what that means is we're going to put an indicator up here on the top of the actual part, and we're going to rotate it by its datum or the thread in the lathe. And we're going to see how wobbly it is. So if the indicator moves more than 0.03 of an inch, it's got too much wobbliness for this design. The engineer decided that 30 thou, well, I'm the engineer on this one, decided that 30 thou was our limit. And anything more than 30 thou, we'll toss the part and we'll make another one to put it into the assembly. So really you're learning about run out for geometric dimensioning and tolerancing. So GD&T run out tolerance. And you're learning about injection molding this week. And you're doing a little bit of drilling and tapping and facing on the lathes in teams. And you'll have a first article inspection to inspect it afterwards using the optical comparator and the actual lathe for the run out. So you'll inspect run out and then a couple of these radii and then diameters and lengths on the optical comparator. And then we'll have another part done for a Geneva wheel assembly. And week 4, we'll come back and actually use the cast acrylic and we'll laser cut that cast acrylic Geneva wheel. So that's the part. Let me show you SolidWorks real quick. Here's the part in SolidWorks. So you're all probably learning SolidWorks or maybe Fusion. Fusion does the same thing. But what I thought I would do is I thought I would show you how I made the molds or the mold cavity based off my SolidWorks part. So I know you're in SolidWorks class at the same time. So how I actually made the handle is I revolved a sketch. I literally just went ahead. Let me go the other way real quick. I literally created this sketch right here, 80 thou radius, that they're typical. It's basically got a 1/4 inch bottom piece, a 0.5 flat right there, 1.625 overall length, 0.5 diameter. So I basically did one feature. It's called the revolve. You should have learned revolve by now in 130. Definitely probably should have. It's week 3. So at this point, after the revolve, I went ahead and I split it right down the middle of my part. So what I had to do is I had to split this thing right there. And then I scaled it. Why I had to scale it is plastic shrinks as it solidifies. So what we do is you can actually see how much it shrunk when you go to try to put it back in this mold. You can see it's a little bit smaller, ever so slightly. You'll see that when you go to make yours. So this alloy of nylon, this is Bidyne. This alloy of nylon shrinks about 2%. So what I did with my scale tool right here is I scaled it up 1.03. So it shrinks about 2.6% is really what it is. So I rounded up to 3 right there on my scale. So I scale it. Then I decided exactly where I'm going to part it, right down the middle of the part. So you can see that. So it's been parted. At this point, I generate what we call a surface model or a parting surface to basically to show my part. Now, let me show you this real quick. We'll show the parting surface. So I created a parting surface of where it's actually going to split in the mold. At that point, I went ahead and created what we call a tooling split. What the tooling split does is it creates a couple of different pieces here. Let me actually hide that. Let me do that. Let me do that. The tooling split actually creates the mold cavity right there. So now I've actually got this mold cavity right here that I can go ahead, right click, and I can insert that into a new part. When I do, sure. I'm just going to do that real quick. It gives me the mold cavity to make the part. So what I did with the mold cavity at that point, let me go ahead and close this one down at this point because I don't need this anymore. And I'm going to close. What I did with that mold cavity is I ended up creating, let's see here. Let me go find this real quick, this assembly. I guess going to the right class would help, huh? Real quick, right there, week 3. It's in the lab manual. Give me 1 second. I'm just trying to find a file. Geneva wheel, mold B. What I ended up doing then was I took that cavities and I went ahead and I made a full tooling set. So if you look, let me go here to change transparency. Come over here, suppress, suppress, suppress. So I made that mold cavity into an actual mold that would attach the machine. So I went ahead and put the threads on it, the nozzle, basically the round cutout for the nozzle. I went ahead, I made the gates and the runners, and then I made both sides of the thing too. So unsuppress that thing, unsuppress that thing. Give me 1 second. Right click, change transparency. Still got one more thing suppressed. Give me 1 more second. Where is it? Well, either way, hold on. See what we got is we've got basically our mold halves and we got our dowel pins. So there's specific, what I'm getting at is there's specific tools in SolidWorks designed to create molds. So you saw that there, you can create parting lines, you can create shutoff surfaces, you can create the tooling. So literally you design your part, you scale it up to what you need it to be for the shrinkage, and then you design your mold based off that. So that's really how our molds were made right there. And then I went ahead and used the CAM system to go ahead and cut them out. We put them on our machine right there. It's going to be kind of showing you how we use the mold tools in SolidWorks. Now on Canvas, you actually have a mold tools video I put up there, a tutorial. If you're interested in learning more about SolidWorks and how mold tools work, so let me come show you that real quick, and then we'll call it a day, and you can go and work on your assignment in lab. So here we go, 146. So what I've got here is you're going to see in week 3's module, injection molding module, I went ahead and I put the SolidWorks mold tools overview. If you go through that tutorial right there, it'll show you how to use all the mold tools. So now this week in lab, you're going to be going through, you're going to have an injection molding timed quiz, just like last week. So after you watch this pre-lab video, you should be ready to take this timed quiz. That'll be due by the beginning of lab 4. And then you'll also have an in-class assignment. I believe it starts on page 145 of the lab manual. 145 and 146 are done in class. 147 is the first article inspection. So you'll do the in-lab assignments, and then you'll do the first article inspection and turn that in by the end of lab or by the beginning of your next lab number 4. So there's going to be really 2 major things, an in-lab assignment and then also that quiz from this pre-lab video. So hopefully you've learned a lot about injection molding from me, and you're going to learn more when you get to lab. If you have any questions, stop by either your lab instructor's office hours or my office hours. We'll be more than happy to answer any of your questions. I hope you have a great week, and I'll see you next week for a non-traditional manufacturing processes. So we're going to talk about laser cutting and some other cool non-traditional processes. Have a great week, everybody.